Yes, today's topic, as per the syllabus, we just moved to the extension of the three-phase induction motor. So we have to take one 2 marks question, which is called the concept of slip, and then moving forward to the torque equation of the induction motor. So in the external examination, you might get working principle of three-phase induction motor or torque equation of induction motor. So what exactly this concept is, we are going to discuss. Right. So if you see the induction motor, what we have studied, induction motor contains stator and rotor. Now you are able to see the animation of the rotor. So rotor rotates, but how the rotor rotates, the rotating magnetic field moves from stator to rotor and cuts the rotor conductors. So this animation is highlighting the rotating magnetic field, which is rotating, and even the rotor, which is also rotating. But in practice, the speed of the rotor, which you are able to see the machine, the speed of the rotor is less than the speed of rotating magnetic field. Rotating magnetic field we cannot see with our eyes, but we can we can see the speed of the rotor. So always the speed of the rotor is less than the speed of rotation of the rotating magnetic field, which is called as the slip. So in an induction motor, there is always a concept called slip, which is the difference between the rotating magnetic field speed and the actual speed of the rotor. So if you see the explanation, this is the 2 marks question. So we know that induction motor contains stator and rotor. The difference between synchronous speed. So what do you mean by the synchronous? As it is rotating at maximum speed, we call it as synchronous. Synchronous speed, ns of rotating magnetic field, and actual speed is called the slip. Okay, so these are the extra points here. Slip increase with load, torque production, right? So this paragraph is quite sufficient. The difference between the synchronous speed of rotating magnetic field and actual speed of the rotor is called slip. So slip formula is ns minus n by ns into 100%. We say that in the induction motor, rotating magnetic field rotates at synchronous speed, ns equal to 120 into f by p. Rotor also rotates, both rotate in same direction, but the speed of the rotor is less than the speed of the rotating magnetic field, which is called the slip. So now with this concept, we just move to the losses in an induction motor. So what are the losses actually? We got the machine. When the machine is rotating, it has got certain mechanical losses. So let us have a look at this particular slide. Let me share this slide. So this is again a simple external question. What are the different losses in an induction motor? So in order to study, we must draw this diagram as it is in the examination. So first we do write the synchronous speed. That means in induction motor, we got stator and rotor. When power supply is applied to the stator or stator windings are excited by three-phase input supply, what's going to happen? Rotating magnetic field is created. Okay, that rotating magnetic field rotates at synchronous speed. The speed of that magnetic field is given by 120 into f by p. Why it is 120 into f by p? We have seen in the working principle. So speed. Now, just now we have taken the slip definition. Ns minus n equal to slip, and actual speed of rotor is always less than the synchronous speed of rotating magnetic field. Remember, slip value is always less than 1. So what is this topic? Just explaining what are the different losses present in an induction motor. So this diagram is quite sufficient. So when three-phase supply is applied to the stator, rotating magnetic field is created. So rotating magnetic field, now it is represented as the power P2, power input to the rotor. So the another name of losses in an induction motor is power stage diagram, which says that each and every behavior of the induction motor is represented by the power. So input power is PIL, as the induction motor converts electrical energy to mechanical. Input electric power is PIL. When input electric power is applied to the stator windings of synchronous induction motor, what happens? 100% of energy is not transferred to the rotor. 10% of losses will be seen. So that's why we are supposed to show certain losses are present within the stator. Next, when input power is applied to the stator windings, rotating magnetic field is created. This rotating magnetic field rotates at synchronous speed ns equal to 120 f by p. That rotating magnetic field is represented in terms of power as power input to the rotor P2. Rotating magnetic field moves through the air gap between stator and rotor. It interacts with the rotor, then current flows through the rotor conductors. We come across the rotor copper losses because rotor has got the copper windings. The rotor copper losses. Now, when rotor is rotating, let us say I want to move one lift system. Inside the lift, we place this induction motor. So, lift means here we represent by the load. Okay. So, for civil engineers, any building is present. Building has to be rotated. That building floors can be connected here. Nowadays, in the news house, we have seen the buildings have been lifted and they are placed in another position. So, any mechanical element which has to be moved from one place to another place, it can be connected to the rotor through the shaft. So when you connect mechanical devices, you come across the mechanical losses. So here we write mechanical power developed is the PM. Okay. So this diagram, and when if any mechanical device is moving, then we say we are doing certain useful work. So we call it as the useful power or shaft power. Right. So this is a simple topic, only the diagrammatic part, but these lines are important. So input we are applying, when you apply an input to any type of machine, you should get the output, but we'll never get 100% output. We get output with certain losses. So input is equal to output plus loss. So same formula, mathematical output equal to input minus loss. Okay. Now the same expression, input power is equal to, what is output here? Output power first stage P2. Input power equal to P2 plus stator losses. Applying the equation at this point. Okay, input equal to output plus stator losses. But what is output? Input minus stator loss. So here you can apply. So input equal to output plus losses. So P2 is equal to PM plus rotor copper loss. But what is PM? In P2 minus rotor copper loss. Similarly, you can easily explain what is P out. P out is equal to PM minus mechanical loss. Right? So for the external examination point of view, if at all you are getting explain the losses of a three-phase induction motor or power stage diagram, this particular explanation is quite sufficient. Now we just move to the most important, toughest part is the derivative part. Let us check this one. The torque equation of a three-phase induction motor. So we modified the derivation as simple in a simple manner. So if at all you are not getting any working principle of three-phase induction motor, you are going to get the torque equation. Now you see the torque equation of induction motor. Now what is the torque actually? Yes. So let me show you this slide. For this torque word only, we have created this animation in order to explain the torque. Right. See, if an object is moving in linear motion, then we confirm that object is moving from one place to another place. Certain work is done by the object. Now, if any object is constant and rotating about its own axis, that means if you see the motor, it is constant at its place and it is rotating in circular direction. Any object, if it rotates in circular direction with a fixed point, it develops a rotational force. So when this rotor is rotating, it develops a rotational force. That rotational force developed by the motor or the rotor is called the torque. So as an engineer, we have to calculate the torque. So in simple terms, rotor is rotating, yes, it rotates with certain speed. Okay, but what is the force created by that particular rotor? That means if I am connecting one particular movable object to this rotor, what is the speed of that movable object? So how much amount of force is applied on that object? It is nothing but the torque. So what is the torque definition? The rotating objects develop certain force. That force is nothing but the rotational force, which is technically called as the torque. So now as an engineer, we have to prove the derivation. We have to derive the derivation of the torque. Now you can see torque equation of a three-phase induction motor. So as three-phase induction motor rotates continuously, we have to prove the mathematical proof of that rotational force. So now you see the very simple first line, torque, okay, T depends on here magnetic flux symbol means rotating magnetic field, because according to the working principle, rotating magnetic field is developed across stator. It rotates through the air gap between stator and rotor. It cuts the rotor conductors, then current flows through the rotor conductors. So rotor means we are representing by 2 suffix. Stator means 1. Okay. So torque developed by the induction motor. External examination also you can write the simple words. Torque developed by the induction motor depends or directly proportional to rotating magnetic field and rotor current multiplied by quality of power transferred from stator to rotor. Quality of power is represented by cos theta to mathematical. So we take it as a constant. T is equal to K into magnetic field into I2 into quality of power transfer from stator to rotor. I hope this equation is quite sufficient. So what is the torque equation of three-phase induction motor? T is equal to K into magnetic field into I2 into cos theta 2, where I2 is the rotor current. Now, so we should not leave this one. So we have to bring the expressions in right. So how to bring the expression? So we must bring the formula for the magnetic field now, current and power factor. This is cos theta 2, so cos theta 2, right? So here if you see E2, what is the E2 here? See, we got rotor and stator. Let us assume E2 is the rotor voltage. I'm making it short explanation for you people. E1 is the stator voltage. Okay, so any voltage, as we have studied, rotating magnetic field links or cuts the rotor conductors. So because of rotating magnetic field only, E2 is developed. You can see here E2 depends on rotating magnetic field. Okay, therefore in the place of rotating magnetic field, we can assume and we can represent T is also directly proportional to E2, I2 cos theta 2. Okay, as E2 is created because of rotating magnetic field. Now, so E2 behavior is similar to the E1, which is the stator voltage. Now, let us take this one. We can also write T is equal to K E2 I2 cos theta 2. Now, you see here, all of you, the current, we already know. Now, I am bringing the definition of the current. Current I is equal to V by R. Everybody know I is equal to V by R. But if I am having only resistors, we can write V by R. But in a room, if I am having fridge, if I am having fan, I cannot write what is the current flowing through the room. I is equal to V by R. We must write I is equal to V by Z. Z is the impedance. I think in the first unit, we have done definitions of the reactance, impedance. You must study that one. So, impedance is the total opposition to the current, AC current. So, I is equal to V by Z. Here we are having the voltage is E2. Therefore, I2 is equal to E2 by Z2. Okay. So, what is Z? Z is the vector combination of resistance and reactance. So, when it is vector combination, we take the square root as well as the square. And these two are perpendicular to each other. So, I2 is equal to E2 by Z2. Similarly, the quality of power transferred from stator to rotor, that is how much amount of magnetic field is transferred from stator to rotor, is given by cos theta 2, which is the whose formula is R2 by Z2. So just substitute the value formula for Z2 and substitute in the formula. So what is the formula? Torque is equal to K E2 I2 cos theta 2. Just multiply. Okay, we get this expression. So remember all of you, torque equation of the induction motor is given by, you can write it as K into E2 square R2 by R2 square plus X2 square in a simple terms. If you want, you can write the mechanical constant value 3 pi 2 pi minus, or else you can live up to this particular derivation. So torque is equal to K into E2 square R2 by R2 square plus X2 square. So this derivation is quite important for the external examination point of view. Right. Let me share the next one as we are taking the topics here. Speed control of the induction motor. So our target is what are the different questions might be asked on the three-phase induction motor. This slide is what is the proof, the last one. Speed control. So what is this topic, speed control? Induction motor is rotating. Okay, imagine induction motor is placed inside the lift. So you are going to approach the first floor, second floor, third floor. So that speed has to be controlled. So this is the induction motor we are having. Okay. So what is the technique name? How to control the speed of the three-phase induction motor? Already I mentioned three-phase means three different wires are displaced by an angle 120 degrees windings. Okay. So variable frequency. We change the frequency. By changing the frequency, we can control the speed of the motor. So you must draw this simple diagram. No need to show this operator interface. You must draw the sine wave power, variable frequency controller, and then which is applied to the motor. Motor rotates at different speed. Simple diagram and simple theory followed by simple equation. The speed control of three-phase induction motor is done by variable frequency control. So what is how to explain this topic? What is variable frequency control? So remember the formula. First, voltage formula is V is equal to I into R. But now, when a machine is rotating, the voltage formula is modified. Voltage equal to frequency into magnetic field. Frequency into rotating magnetic field for induction motor. Now, from this expression, frequency is, we can write F is equal to V by Q. That is, frequency is inversely proportional to magnetic field here. Inversely proportional to magnetic field. As frequency increases, magnetic field decreases. Okay. So now what you are trying to explain. Now case 1 we will take here. So you must write this point. Case 1, at low frequency. At low frequency, that is, when frequency is less, what's going to happen? Magnetic field is maximum. Okay, magnetic field increases. So with low frequency condition, magnetic field will be increasing. The speed of the induction motor also increases. And reverse case. Reverse case. So if frequency increases, what's going to happen to magnetic field? Magnetic field decreases, and hence the speed of the machine. Speed of the machine decreases. Okay. As the magnetic field decreases, the speed starts to decrease. So case 1, I repeat once again, case 1 is if the frequency is very much less, frequency is inversely proportional to magnetic field. If frequency is less, for low frequency conditions, the magnetic field strength increases and hence the speed of the motor increases. Okay. Case 2, for high frequency conditions, the magnetic field strength decreases and hence the speed of the motor also decreases. So for high frequencies, the motor rotates with low speed, and for low frequencies, the motor rotates with the different speed. Okay. So V is equal to F into Q. F is inversely proportional to magnetic field. From this expression, we can assure that as the frequency increases, magnetic field decreases. Okay. But here variable frequency control, in-depth explanation, we are at constant V by F technique. That means you can see this expression. Case 1. Okay. Now I am just modifying the explanation. Right. Case 1 is, let us say, at low frequency. I am just not writing here. At low frequency, what's going to happen? Magnetic field increases. Okay. When magnetic field is increasing enormously, the motor saturates. Saturates means entire machine is filled with the maximum magnetic field. Under this condition, the motor gets heated up. So this magnetic field increase should be controlled. Therefore, if you see once again the mathematical equation here, voltage is directly proportional to magnetic field. So whenever magnetic field is increasing to a maximum value, the voltage again it should be decreased. Okay, then the magnetic field will be maintained constant. Right. So this is what a simple explanation of the speed control of the induction motor.